Unit 1, Lesson 6, Derivative Rules. The entire first half of calculus is differential calculus, so being able to properly take the derivative is huge. We reviewed power rule and some of the trig functions that you need to have memorized, but now we need to go over product rule, quotient rule, and chain rule that you guys learned in pre-calc. So first, product rule. Let's let u and v represent differentiable functions u of x and v of x, and we'll just abbreviate them u and v. If you're trying to take the derivative of u times v, product rule says take the first times the derivative of the second plus the second times the derivative of the first. So using prime as the derivative notation, uv prime plus vu prime. Quotient rule is for when two functions are being divided. If you need to take their derivative, we're going to do low d high minus high d low all over low or low squared. And our third rule is the chain rule. This is our outside-inside rule. It's because this is for functions that are compositions of one another, meaning that v of x is inside u of x. So when we're taking the derivative, we can only do one at a time. So we start with the outside derivative. We do u prime, and we leave v of x composed inside there. So we leave v of x on the inside. And then you zoom in. Now it's like, okay, we've already taken care of the outside. Now we're going to zoom in to the function that was inside the other and take its derivative. So then we would multiply by v prime of x. This is our outside-inside rule. Now, with chain rule, sometimes there are multiple levels. So I'm going to just put this for our notes for a second, and until we get to an example, it might be a little confusing. The chain rule is our PTA rule, and it's because often chain rule shows up where there's some trig function raised to a power. So this stands for power, then trig, then angle. We'll go over it again when we get an example like it. Our next slide here is a flow chart for selecting a procedure for derivatives. One thing that is going to happen is that you need to be smart about how you take the derivative, especially with product rule and quotient rule. You don't always have to use product rule and quotient rule. Sometimes there's an easier way, meaning the function can be factored and reduced, simplified in some way. Maybe you don't have to go through the whole product and quotient rule. So this is just a little flow chart to kind of train you in how to think about what rule do I need. So first look at it and get a sense of, well, what kind of function is this? Now, if it's a quotient or a product, you want to think about, before you do anything, can I change this into a different form? Can I factor and reduce? Can I distribute? Can I cancel something out? If no, then you're just going to take the derivative. If yes, do that. Make it easier. Simplify the function, then go back through the process. Now, if it's not a quotient or a product rule, is it a composition? Is it a function within a function? If it is, that's going to be a chain rule. If it's not, maybe it's just a basic function, meaning it needs power rule, or you should have it memorized. This flowchart is really for when you first get the sense that you need a product or a quotient rule. Take the extra second to say, can I change this into an easier form? It'll be a huge tool if you train yourself to think that way. Now, when we look at the examples, I know that you guys learned how to take derivatives last year. So today, instead of just practicing take the derivative, we're going to start applying them right away. So number 4 asks us to write the equation of the tangent line and the normal line to the graph of this function f of x at this point. Now, to write the equation of a line, you need two things. You need a point, got that, and you need the slope. So I need the slope of the tangent line. Well, that's the derivative. The derivative is the slope of the tangent line. So let's take a look at our function f of x. And we've got two options here. This could be a product rule, where this is my u, this is my v, or I could FOIL this out and distribute. If I distribute, I don't need the product rule. I would argue that either way is the same level of difficulty, so I'm going to choose to do product rule for our derivative. So, u v prime. So u as itself means I keep x minus 1, and then v prime is the derivative of x squared minus 2, plus v as is, then u prime, so times the derivative of x minus 1. Now what we're looking at here is the derivative at any x. Well, we're not at any x, we're at this coordinate point 0, 2, and more specifically, we're at x equals 0. So I need the derivative at 0. So everywhere there's an x, replace it with a 0. 0 minus 1 is negative 1, 2 times 0 is 0, plus negative 2 times 1. So we've got 0 plus negative 2, which is negative 2. The derivative at 0 is negative 2. This is the slope of the tangent line. Now I have everything that I need. I have a point, 0, 2, and I have a slope of negative 2. So I'm going to use the point slope formula of a line. Y minus y1 equals slope, parentheses, x minus x1. And we're going to plug it in. Y minus the y value of 2 is equal to the slope of negative 2 times x minus 0. Now, we don't have to simplify anything, so I could really say that this is my tangent line, or if you did want to simplify, or if it was a multiple choice question, then we could say mx plus b form, that our derivative, or the tangent line, excuse me, is negative 2x plus 2. Either way, this is the equation of the tangent line. Now, what is a normal line? A normal line is perpendicular to the tangent line. Very often normal lines are looked at in things involving optics or light, the way things are reflected. So sometimes you might want the equation of a normal line. And perpendicular lines have negative reciprocal slopes. So I'm going to look back up here at the point slope formula version of the line and just change my slope to the negative reciprocal, a positive 1/2. And be careful with the normal line. You do want to go back to the point slope form, not your mx plus b. This one happens to have the same y-intercept since our x value was 0, but that's not always the case. So make sure that you change it in the point slope formula. Number 5, determine the point at which the graph of the function has a horizontal tangent. Well, horizontal lines have a slope of 0. Now the slope is the derivative. So this is really asking me, where is the derivative 0? Because that's what's going to make a horizontal tangent or a line with the slope of 0. So looking at our function, we have a quotient rule. And unfortunately, there is nothing we could do to factor and reduce. On the bottom, we have perfect squares, but it's plus. So we have to do quotient rule. Low d high minus high d low all over low low, or low squared. And I want to know where this derivative equals 0. Now, since we're working with a fraction, the numerator of a fraction, if that's equal to 0, then the whole thing is equal to 0. If the denominator of the fraction is 0, it's undefined. We actually want this to be equal to 0, so I could just set the numerator equal to 0. As I'm doing that, though, I'm going to simplify because I have to distribute and multiply. So we have 2x cubed minus 2x cubed. That's what I want to set equal to 0. I can cancel like terms, and dividing, this should be a plus, dividing both sides by 2, we still wind up with that x is 0. Now, there's a little bit of a snag here, though. The directions asked for the points. Points are not x values. Points are x, y values. So, how do I get the point? We're going to have to plug into the original f of x to get any y values of the function. So now that we know the horizontal tangent is happening at x equals 0, then I want to know what is the y value, meaning what is f at 0. As it turns out, this y value is also 0. So our final answer is that the point 0, 0 has a horizontal tangent line. The next few examples are just a few challenges in terms of practicing taking the derivative. So number 6, at first glance, it looks like a product rule, but it would be a product rule and a chain rule. So instead of doing a product and a chain rule, I think that we should simplify this. A negative exponent would shoot that second expression into the denominator. And now I can just use a quotient rule. Low D high minus high D low, all over denominator squared, or low squared. Now, free response question. This takes practice to actually just leave it. You don't have to simplify this. So if it's free response, take the derivative and walk away. All right, let's look at number 7. Number 7 here, we're going to actually have to do two different things. In this first part, I've got a product rule, 2x times cos x. But then subtraction separates these terms, and we've got minus 2x. So we've got to start with our product rule. dy dx is another notation for derivative of y besides y prime. So let's just practice using our different notations. And we would start off with u v prime. Now I told you to memorize the derivative of cosine. So that's negative sine x plus v, which is cosine as is, times u prime, which is 2. Now I'm at the point where I'm going to bring down that minus sign. This next term, 2 sine x, you could argue that it's a product, that it's the constant 2 times sine x. The deal is, though, when you take the derivative of a constant and you're just thinking of it by itself, it goes to 0. So there's something called the constant multiple rule, and basically it allows us to ignore the second half of the product rule, that we would just say our u, which is 2, v prime, the derivative of sine is cosine, but then I don't have to write out the second part of the product rule, which would be v sine x times the derivative of 2, which is 0. That's going to cancel out. So whenever you have a constant, you could just keep the constant times the derivative of the function next to it, and it's basically ignoring the half of the product rule that goes to 0. Now, we can leave the answer just like this. But sometimes you might notice something that's so hard not to cancel out. At least for me it is. We've got this cos x times 2 and then minus 2 cos x. They do just cancel. You are allowed to cancel if there's something that's really just jumping out at you. But again, you don't have to. And again, since I'm already rewriting because I made this point, I just kind of reordered this term so I didn't need all the parentheses. And this would be my simplified derivative. All right, number 8. Yikes, this is a quotient rule because we're dividing, but then we've got product rule on the top and product rule on the bottom. Definitely not the most efficient way to do a quotient rule with two product rules in there. So let's FOIL out the top. We've got x squared, and then 2x plus 1x gives me a 3x plus 2. Now I've avoided that product rule. Same thing on the bottom. We've got x squared minus 3x plus 2 in the denominator. Now I can just do a quotient rule and not worry about the two product rules. So we've got low d high, that's going to use our power rule, minus high d low, all over, oops, that's minus sign, low squared. I am glad this one is free response, that I don't have to tackle this algebra. I do not have to simplify anything. That's my derivative. Number 9, we've got another quotient rule. So our derivative, dy dx, low d high, the derivative 1 is 0. The derivative of negative cosine, well, that's going to be positive sine. Low d high minus high d low, derivative of sine is cosine, all over low squared. I'm going to get fancy here. Remember, when you're squaring a trig function, instead of putting it in parentheses, you can move the squared in between the trig function and its angle. So here's our derivative. We don't have to simplify. All right, number 10. Yikes, we got a complex fraction. Well, we're going to need a quotient rule, but I want to take a second and simplify this complex fraction. Instead of taking this derivative with the complex fraction, let's go through and say, all right, to simplify this, I could multiply all of the terms by the common denominator, x. So if I go through and multiply everybody by x, Ah, that looks a lot nicer to do a quotient rule on. Now I can say low D high minus high D low all over low squared. And here's my derivative. All right, let's take a look at number 11. Suppose that u of x and v of x are both differentiable functions of x, and then they give us this information about u prime, v, and v prime, and asks us to find the value of the derivatives at x equals 1. I like to take this information, since it's all at x equals 1, and just kind of organize it into a table. So now that we have it organized, part A is asking us for the derivative of u times v. Now remember, u and v are both differentiable functions, so this needs product rule. u v prime plus v u prime. And now just using our table, we can plug in u is 2, v prime negative 1, and then v is 5, u prime is 0. So negative 2 is our solution. Let's look at b, the derivative of u divided by v. So we've got low d high minus high d low all over low squared. Now let's use our table and plug in. We've got v is 5 times 0 minus 2 times negative 1 all over 5 squared. So our final answer, 2 over 25. C is also a quotient rule, but now our denominator is u. So low d high minus high d low all over low squared. And let's plug in 2 times negative 1 minus 5 times 0 all over u, which is 2 squared. So we get negative 2 over 4, which obviously simplifies. Negative 1/2. Again, though, you didn't really have to simplify because it's free response. Part D, the derivative of 7v minus 2u. Well, we don't need a product rule when you're doing a constant multiple, so it's just 7v prime minus 2u prime. So 7 times negative 1 minus 2 times 0. So negative 7 is our solution. Number 12, find the equation of the tangent line to the curve. Well, look at this. We've got y equals 2 minus x over 5 plus x. So we're going to need the quotient rule because the derivative is the slope of the tangent line. Okay, so now we've got low d high minus high d low all over low squared. Now this is the derivative at any x. We don't want the derivative at any x. We're actually being asked to write the tangent line when x is equal to 1. So let's replace all of these x's with 1's. So 6 times negative 1, then we've got 1 times 1 over 6 squared, which is 36. So I've got a slope of negative 7 over 36. This is the slope. But we need two things if we're going to write the equation of a line. We need the point and the slope. So I also need the y value when x is equal to 1, so I could get the xy coordinate. So let's plug 1 in for x into the original y, and we've got a y value of 1/6. So the coordinate point is 1, 1/6. Now I can take these two pieces, the point and the slope, and write the tangent line using the point-slope formula of a line. Y minus 1/6 is equal to 7/36 x minus 1, and this is our tangent line. So don't be freaked out by fractions. They're fine. All right, number 13, this is a great one. This is one of my favorites because this is something that a lot of people get confused with. The function is sine of cosine x. We want the derivative. The hardest part about this is that this is not a product rule. Remember, sine all by itself, that doesn't mean anything. You have to take sine of an angle. take a second, press sign on your calculator. Notice it comes up with an open parentheses. It's asking you of what? Sine by itself doesn't mean anything. So this is a chain rule, sine of cosine. So our chain rule is our outside-inside rule. First, I'm going to take the derivative of sine, which is cosine, but I'm going to leave of cosine alone. So that looks so weird, cosine of cosine, but that's what it is. Then we zoom inside and say, all right, times the derivative of cosine, which is negative sine x. Now we have to take a second and find that in our choices, and here it is, choice A. All right, number 14, it wants the y-intercept of the tangent line to the curve y equals square root of x plus 3 at the point 1, comma 2. So a little bit of a curve here that they want the y-intercept. So first thing I need to do, though, is write the equation of the tangent line. So what do we need? We need a point, check. We need the slope. The derivative is the slope of the tangent line. So how am I going to take the derivative of y equals square root of x plus 3? Well, what we need to remember is that square root is the 1/2 exponent. So this is a power rule. We're going to take this 1/2 exponent, multiply it down to the front, leave the x plus 3 inside the parentheses, and subtract 1 from the exponent. Then we have to zoom in and multiply by the derivative of the inside, and the derivative of x plus 3 is just 1. Let's take a quick second to simplify this. A negative exponent is going to shoot this down to the denominator. So we've got 1 over 2 times x plus 3 to the 1/2 power as the derivative at any value of x. But I don't want the derivative at any value of x. I need to evaluate the derivative at x equals 1. So now we can plug in 1 for x. 1 over 2 times 1 plus 3 to the 1/2, which is 1 over 2 times 4 to the 1/2. Now remember, the 1/2 power is just square root. So this becomes 1 over 2 times 2, or in other words, 1/4. But 1/4 is not the y-intercept. 1/4 is the slope of the tangent line. So in order to get a y-intercept, we need the b part of y equals mx plus b. So we need to get our line in mx plus b form. So I have a point and I have a slope. So let's use our point-slope formula of a line to start writing our equation. We've got y minus our y value, which is 2, is equal to the slope 1/4 times x minus our x value. But we're not good with point-slope formula this time because we need the y-intercept. So first we're going to distribute the 1/4 and add over the 2. So Unit 1, Lesson 6. Negative 1/4 plus 2 is like adding 8/4. So 8/4 and a negative 1/4 would be plus 7/4. And now we know our y-intercept is 7/4 because we've got mx plus b form. Number 15 gives us a function f of x, and it asks us to find the derivative. Now, first glance, this looks like a product rule, but we also have a chain rule in here. Can I do something to simplify this? And the answer is no, not really, because taking x plus 2 and cubing it is not really simpler than mixing a product rule and a chain rule. So I've got to start with the first rule that I see here, which is product rule. I am multiplying two things together, so x plus 1, that's going to act as our u, and our x squared plus 2 to the third, that's going to be our v. So we've got u. Now v prime, this is a chain rule. We have to start with that cubed on the outside, multiply the 3 down, leave the x squared plus 2 alone in there, subtract 1 from the exponent. But now, since this is a chain rule, we're going to zoom in and take the derivative of what's inside. So the derivative of x squared is 2x, and then the 2 goes to 0. So Thinking back, this was u. All of this here was v prime. Now finishing the product rule, I've got to do plus v u prime. And the derivative of x minus 1 is just 1. Now, this would be great if we could look over at the multiple choice answers and see that answer, but we do not. This is how a multiple choice question is going to force us to simplify. So let's start seeing what we can do here. I am noticing that on this first term, I've got this 3 and the 2x here. So let's multiply that together to be a 6x. Then I've got the other pieces coming down, x minus 1, x squared, plus 2 squared, and anything times 1 is just itself, so we've got x squared plus 2 cubed also coming down here. Now, this is still not any of our choices. I want you to remember that when you're looking for a greatest common factor, it doesn't always have to be a single term. Look at both of these have x plus 2 to some power, so I can pull out an x squared plus 2 squared as a greatest common factor. So I'm going to set up parentheses then. If I pull this x squared plus 2 squared to the front, then I'm left with these two terms on the inside, 6x times x minus 1, and then plus, well, I was only able to pull out squared to the front. So I would have one more, or x squared plus 2 to the first, left on the inside. All right, still not a choice, but I'm starting to see a couple that are shaping up to look okay. We need to simplify inside our parentheses. I can distribute 6x, and then really there's like a 1 in front of these parentheses, so I can just remove those parentheses, distributing that 1. And now we've got some like terms that pop up, 6x squared and 1x squared combined. And yay, we finally found our answer, choice D. All right, let's look at number 16. It's just asking us to differentiate, which means take a derivative. But part A is one of the ones that tend to get people when they're trying to decide what rule it is. And this is what I was referring to when I said the chain rule is often going to follow the PTA pattern. P standing for power, T for trig, and A for angle. Because when you're using a chain rule, you can only do one thing at a time. Now, this cos squared, what that's implying is all of cosine x cubed is being squared. So if we rewrite it to remove this shorthand notation, we can really see that the outermost function is that exponent, or the squared. And that's why we start with the power for PTA chain rule. So let's start by multiplying down the 2 and then subtract 1 from the exponent. But remember, only one thing at a time, so nothing changes with this cos x cubed on the inside. We're then going to subtract 1 to the first power, which you don't have to write, but I just wanted to show you what I did. Now I zoom in one level, and the next level of this is the cosine function. That's why trig comes next. So now I'm going to take the derivative of cosine, and this I have to have memorized, so the derivative of cosine is negative sine, but we always have to take the sine of something, so we leave in there the x cubed. I can't take a derivative of x cubed yet, it's one piece at a time, and all I was doing there was the trig part. Now lastly, I can take the derivative of the angle. Remember, we take sine, cosine, and tangent of angles, so x cubed is representing the angle that we're taking the cosine of, or the negative sine of, in this part of the function. So the last piece is to multiply by the derivative of x cubed, which is 3x squared. And now I've hit the power trig angle, or PTA chain rule. Just for practice, if I needed to simplify this, the only things that multiply together here are the 3x squared. This is like a negative 1 and the 2. So I would be able to rewrite this as negative 6x squared Then we can put the cosine x cubed, but I don't need to that first power anymore, so I'm going to drop that out. And the sine of x cubed, and we took care of that negative sign by multiplying it to the first term. So simplified, this is our derivative, although we don't have to do that unless it's multiple choice. So for part B of this question, I want to rewrite the original function again. This is saying 3 tan, and then we're taking the tangent of square root of x, which in order to see and take its derivative, I want to think of that as x to the 1/2 power. But that square root is only on the x, so that's inside the angle there. Taking the derivative, even if we want to follow the PTA model, there is no power, meaning there is no exponent that's being applied to the tan function. So we can skip right to the trig part, which is tangent. Now, 3 is in front here. I don't need a full product rule, though. I could just use the constant multiple rule, which keeps the 3 and then multiplies it by the derivative of the function next to it. So derivative of tangent is secant squared. That's something I have to have memorized, and I leave the x to the 1/2 on the inside. Then zoom in and take the derivative of our angle, or the x to the 1/2. That's a power rule, multiply down the 1/2, subtract 1 from the exponent. Again, we don't have to simplify for free response, but let's just practice it. A negative exponent would shoot that down into the denominator. Those 1/2s are really radicals, so fully simplified, we'd have 3 secant squared of the square root of x, and then 2 times square root of x in the denominator. It's good to practice simplifying for multiple choice questions, but the way the lesson is written, I really could have left the answer just like this. And finally, number 17. Assume that h of x is f of g of x, where both f and g are differentiable functions. Then they give us some information about g, g prime, f prime, and they ask us to find h prime at -1. Well, before we find h prime at -1, the first thing that we need to find is h prime of x. Now, since h of x is a composition, f of g of x, this is really a chain rule. And you're definitely going to have to write chain rule out in notation form, meaning the derivative of the outside, so f prime, keeping g of x on the inside, then zooming in and multiplying, that's meaning to be a dot, not subtraction, by g prime of x. I would memorize this. This is the chain rule as a rule, and it is something that comes up all the time. So be very comfortable with writing the chain rule as a rule. Now we could say that they want h prime at -1 and replace all of our x's with -1. So let's simplify. We need g at -1. G at -1 is 2. Then we need f prime at 2. That was given as -4. Then g prime at -1. G prime at -1 is given as 3. So our final solution is -12. Great work today. Good luck on the Delta Math practice.